Hi, everyone. My name is Zoe Z. First of all, I'd like to thank the organizers for putting on this excellent conference. It's really an honor to be invited to talk about the group's latest results. So we just heard an excellent talk from Mike about how molecules can be leveraged to perform tests of fundamental physics. And today I'll be telling you about results that are coming from a kind of orthogonal motivation, which is to use diatomic molecules to simulate complex quantum many-body systems. And to do that, we use the technique of quantum gas microscopy. Before I get started, I would like to acknowledge the team. This work was done by the supervision of Professor Wasim Baker and was carried out in the lab by grad students Lysander, Jason, Ravin, and former members Elmer and Sungjae. And I'd also like to acknowledge our theory collaborators, Alan and David. So many of us in this community know and love ultracold atomic gases because there are many tunable degrees of freedom in our quantum toolkit. For instance, from cold atoms, we know and love the ability to tune density. These ensembles are defect-free. We can choose the quantum statistics by choice of species, for instance. You have all of that and some more with molecules. Primarily, molecules have a richer set of internal degrees of freedom, including vibration and rotation of the nuclei, and that gives rise, in certain cases, for polar molecules, to be able to manipulate these using external fields, such as DC electric fields and microwave fields. And very crucially for our application, you can have these tunable, long-range, anisotropic dipolar interactions which are at a much higher energy scale than the typical contact interactions that you would experience with most neutral atoms. And as was touched upon briefly by the last speaker, there have been two complementary approaches in the past decade and a half or so for forming these ultracold molecular gases. So one was pioneered in 2008, basically is association of molecules in a coherent fashion from already pre-cooled cold atoms. And this has spawned countless works around the world, maybe on the order of tens of groups now have achieved ultracold bialkalis in their absolute ground state. And recent highlights include the formation of degenerate fermionic molecular gases by the group of Junyi and Emmanuel Bloch. So the advantages for this approach are that you can achieve incredibly low temperatures, including degeneracy. You can study itinerant physics because the motion is very well controlled, and you have large numbers of molecules, even to the 10,000s or hundreds of thousands. In more recent years, there's been a exciting new development with molecular tweezer arrays, which we'll hear about more tomorrow as well. And basically, the advantage here is that you have single molecule detection and control with each individual molecule trapped in a single optical tweezer. And these can be laser cooled, they can be bialkalized, but a key advantage is their rapid cycle time. However, the motion is a little bit harder to control. Many of these examples are motionally hot, so these would be very suited to studying, for instance, spin physics. We like to combine advantages of both approaches, both the large number, the ultra-cold temperature, and the motional degree of freedom, everything in the motional ground state, with the single molecule detection and control capability afforded by another technique. And the way we do that is we borrow a technique pioneered on atomic gases, which is called quantum gas microscopy. So by now, there have been many species of atoms around the world. This is probably no longer a comprehensive list that have successfully been imaged with quantum gas microscopes. And all you need to understand is that you can trap these atoms in a single two-dimensional layer in an optical lattice, allow these atoms to fluoresce, collect that fluorescence in a high numerical aperture objective, image it on the camera, and recover these beautiful images, single shot, of the atomic wave packets. And so we would like to do that for this sodium rubidium molecule. It's a bosonic species. It has been previously brought into its absolute ground state by pioneering work done by the group of Da-Jun Wang at Hong Kong. And we choose it because it has a relatively large and healthy dipole moment in its ground electronic state. Very briefly, how do we form these ultracold molecules? We start off with magneto-optical traps of rubidium and sodium, both nicely visible in our lab. And through a successive series of magnetic evaporation, optical evaporation, we end up with a gas of the two atomic species, which we want to trap in a very tightly confined two-dimensional layer for microscopy purposes. So we send in a light sheet potential, we further confine it in a pancake of a vertical lattice, and we tune the relative atomic species number using a bichromatic dimple trap. To form molecules, we first start by turning up a two-dimensional optical lattice shown by this egg crate cartoon, and we coherently associate free atoms into Feshbach molecules, so weakly bound molecules, by adiabatically ramping across a magnetic Feshbach resonance. So every lattice site that has a single sodium and a single rubidium will associate into a molecule with near unit probability. And we can verify that this is the case by performing RF spectroscopy and measuring the binding energy versus magnetic field of the molecule. And you see that these are indeed very weakly bound molecules on order of 10 megahertz binding energies. Here are some images from our quantum gas microscope. So we don't image the Feshbach molecules directly. What we do is pin the molecules, break them apart by reversing the Feshbach step, blowing out the remnant sodium atoms, and performing optical molasses on the rubidium atoms. And the rubidium atoms serve as a tag for the molecule location. So you see on the left an in situ single shot image of rubidium atoms that represent our Feshbach molecules, as well as the digital reconstruction. And here you see the average filling for many images versus distance for both the molecules and the atoms. So although our ultimate goal is to create ground state molecules, our first experiment, we decided it would be fun to measure spatial correlations of these non-interacting molecules to kind of demonstrate the power of the shot noise limited imaging capability that a quantum gas microscope gives you. So if you've heard of this Hanbury-Brown twist experiment, you might expect bosonic bunching correlations between identical bosonic molecules. And let me explain. So in the 1950s, there was a series of landmark experiments done by Hanbury, Brown, and Twist. And this kind of spawned an entire subfield of stellar astrophysics, as well as giving rise to the language of modern quantum optics. So it was a pretty impactful experiment. What they did was send an incoherent light source on a beam splitter, and the light they collected on two different photomultiplier tubes where they could change the relative distance of the two PMTs with respect to the incoherent light source with the translation stage. And they found, to their surprise, that the photons, which are bosons, like to arrive simultaneously on these two PMTs. And in the modern quantum optics language, that is a G2 correlation function, an intensity-intensity correlation function of 2. And as the distance decreases, this goes down to the uncorrelated value of 1. Now, that can all be explained in a semi-classical wave interference picture, at least for the bosonic case. But there is also a very nice quantum interpretation, and that's the fact that if you have two particles, you allow them to evolve and travel for a long distance. You image them on two separate detectors. There are two possible ways that can happen. They either traverse with the black pathway or the blue pathway. And because they're identical, these amplitudes will interfere and cause in the case of 2 particles in a lattice, a sinusoidal oscillation of the G2 function. And if you have more particles, a larger and larger source size, the peaks will become narrower and narrower. And that's mathematically because this joint detection probability is nothing more than the Fourier transform of the initial source distribution. So I'll highlight that there have been many experiments looking at HBT correlations in the cold atom community. So we decide to measure the HBT correlations with ultracold molecules. Again, our experiment is conceptually simple. We start with an in situ sparsely populated gas, turn off the lattice, allow expansion in the 2-dimensional plane, and then turn back on the lattice, freeze the motion, and image the momentum space occupation. So we first benchmark this with rubidium atoms because there we have higher signal to noise. So these are the parameters. This is the G2 function with respect to x and y displacement, as well as a one-dimensional cut through the data. So you see peaks appear where the red arrows are, but the red arrows are not merely a guide to the eye. They're the exact position that we would expect the correlation peaks to occur, given based off of our time of flight, the rubidium mass, and the lattice spacing. So we see high contrast G2 almost to the maximum value of 2, which gave us confidence to repeat this experiment with ultracold molecules. And when we repeat this with molecules, you see the signal is smaller because our molecules are sparser. The peaks are closer together because the molecular mass is greater than the atomic mass, and yet there is still a very high contrast of around 54%, which we can measure. So to conclude this section, we demonstrated the power of the microscope to see really tiny signals. We believe this would not have been possible if we were only looking at absorption images, at least with our molecular densities. So for the rest of my talk, I'll be focusing on work done in the ground state. So we like ground state molecules because the ground electronic state hosts a permanent body frame electric dipole moment. And we create these ground state molecules in what's by now a very conventional way, a 2-photon STIRAP process, which coherently brings all the Feshbach molecules into the ground electronic, vibrational, rotational, and hyperfine state. And we do this with a 94% conversion efficiency. I will say we cannot image the molecules directly in the ground state. We have to reverse STIRAP and then image the Feshbach molecules, as I mentioned before. Our maximum filling right now is hovering around 15%, at least at the time that this figure was produced. And you can see we can image the Feshbach molecules, the ground state molecules, and the average filling drops off with the radial distance. With the molecules in the ground hyperfine state, we can start doing rotational spectroscopy. So here is a very simplified level schematic of the ground rotational, first excited rotational manifold with the projection numbers of the rotational angular momentum. The different wave functions are just the normal s and p orbitals, and I've neglected all of the hyperfine structure here, but these degeneracies are lifted when you include the nuclear spin. So this single molecule Hamiltonian is well known, so we can predict where all of the lines lie and do microwave spectroscopy by applying 4 gigahertz microwave field coupled to our molecules and see absorption of the spin-up molecules, which are our ground rotational state. We can isolate one of these transitions and drive coherent Rabi oscillations as well. Why are we interested in rotational transitions? Well, in the absence of any external symmetry breaking external field, there is actually no lab frame dipole moment, even in the ground state, so that's kind of boring. So we either need a DC electric field or resonant or near resonant microwaves to generate a lab frame dipole-dipole interaction. So n equals 1 and n equals 0 are opposite parity states. So when they're coupled, for instance, if we couple this transition with the sigma minus polarization, we get this rotating peach-like wave function in the lab frame, which corresponds to a healthy portion of the body frame dipole moment of the molecule. Our final ingredient before we do quantum simulation is to test that our rotational coherences are sufficiently long-lived. And we do this with what atomic physicists know and love, Ramsey spectroscopy. So pi-half pulse, precession time, readout pi-half pulse with the option of a spin echo. And we have to choose a near magic B field condition to mitigate some differential light shift. But when we do this, we were very pleasantly surprised. Here are the contrast data for the case without the spin echo in the pink, as well as the case with the spin echo pi pulse in the blue. Now you see that this blue curve is longer, as you might expect, but it still decays over around 200-300 millisecond time scale. However, we considered what the contrast decay should look like for our exact situation with a 1% density, which we were taking this data with, and we see that the blue and the black agree to pretty good precision. So the black curve is exact diagonalization with no experimental imperfections. So this was indicating the loss of contrast is due to many body dephasing. So dipole-dipole interactions, even with as dilutive a filling as 1%, which was basically the lowest we could go without killing ourselves in the lab. And so this was really promising for us because it still seems that 400 milliseconds, we are limited by dipolar effects rather than trivial experimental imperfections. And to our knowledge, this is around one of the state-of-the-art results for molecular rotational coherence times. I will highlight past results, both for rotational and nuclear T2 times have also exceeded 100 or even hundreds of milliseconds for rotational and the second scale for nuclear spin. So with all these ingredients in place, we can start to study various lattice spin models for quantum magnetism using ultracold molecules. So the natural mapping is these up and down states are our pseudo-spin 1/2 states. And a very generic lattice spin model you can write down is the XYZ Hamiltonian with arbitrary X, X, YY, and ZZ couplings. However, the natural Hamiltonian for us is the spin exchange Hamiltonian, where you merely have the XX and YY terms. Here, V is the dipole-dipole interaction, and it's anisotropic, and for us, maximizes at a value of around 1 kilohertz. And I should also point out, there was groundbreaking work done around 10 years ago by the group of Junyi, also studying the spin exchange Hamiltonian in a 3-dimensional optical lattice. So molecules are special because you can tune the interactions based on state choice as well as the orientation of your quantization axis. You can choose by coupling here to have attractive versus repulsive interactions, but everything I'll talk about will be coupling to a predominantly M sub n minus 1 state, so coupling the spherical wave function with this donut. If you orient your quantization axis, set by our magnetic field, perpendicular to the plane, you can immediately see, by virtue of how these donuts are all aligned, that all of the X and Y interactions will be isotropic, and they also happen to be attractive. However, if you orient your quantization axis parallel to the plane, you'll immediately see that there's an intrinsic anisotropy where you have repulsion along one axis and attraction along another. So that's something special that we can play with. First of all, let's focus on the isotropic case. We purposefully dilute our filling and we perform this Ramsey quench experiment again. And we phase shift our last pi/2 pulse so that in the absence of any dipolar couplings, we would never measure any molecules. Remember, we only can image the up spins and not the down spins. However, because we have dipolar interactions, we see that the fraction of ups does grow over time, and moreover, it doesn't grow in a monotonic fashion. There are these bumps, and these bumps are exactly at the frequency you would expect from the nearest neighbor dipole-dipole coupling in our lattice. You can see that initially you see very sparse pairs of molecules starting to emerge, whereas in later times it's like the entire cloud will get entangled and all of them will start to appear, or half of them. And because we're a microscope experiment, we can measure local correlators like this spin-up correlation function, and we see that at early times the correlation versus x and y displacement only shows nearest neighbor interactions. But at later times, we see the next nearest correlations build up, so on and so forth. And we can plot this in a line plot, again, for the nearest neighbors, diagonal neighbors, next nearest neighbors, and we see that the intrinsic frequency does slow down based on this 1/r cubed distance. The theory is from exact diagonalization of our system. So these are the same data as what I showed in the slide previously. I'll highlight that they were isotropic correlations because the interaction potential was isotropic along the xy plane of our lattice. However, as I mentioned before, we can tilt the quantization axis out of the plane, and then our interaction potential is repulsive along x and weakly attractive along y. And the correlations do bear that out, because when you see the x correlations of the nearest neighbors, they oscillate twice as quickly as the nearest neighbor y correlations. And the strong anisotropy is also very apparent in the correlation matrices as a function of time. Final topic for today. I promised earlier that we would be able to access x, y, z Hamiltonians. So where did the z term go? How do we engineer an Ising term in our spin model? So you can do it with a static electric field. We choose to engineer this ZZ coupling term with Floquet techniques. So you can imagine initially you're evolving under an XY Hamiltonian. You perform a pi/2 pulse. You can think of that as a rotation of the block vector, the block sphere, so that you're evolving under an XZ Hamiltonian, and an optional spin echo again, and then another pi/2 pulse along -x will get you back to the original XY Hamiltonian. You repeat this many times, and the whole point of Floquet engineering is that your Floquet frequency must be much faster than the intrinsic timescales of your system. After you do this, and with appropriate choice of timing between your microwave pulses, you end up with this XYY Hamiltonian, which more conventionally, people call this the XXZ spin Hamiltonian. And this is a very famous model in quantum magnetism and is, almost a textbook model in some sense. We verify and benchmark that we've implemented this XYY model first by studying the global magnetization evolution as a function of time. So we can initialize our molecular states along 3 different axes, plus z, plus y, plus x, and watch the magnetization decay as a function of time in the case of plus z or plus y. However, plus x is a unique case because of the U1 symmetry of the Hamiltonian. The Sx operator commutes with the Hamiltonian, so this magnetization is a conserved quantity, which our data also support. And finally, we can measure the spin correlations. And again, the spin correlations for the nearest neighbors, diagonal neighbors, and next nearest neighbors are very similar to what we would expect with theory from exact diagonalization, which gave us confidence that we weren't messing up our Floquet driving. And in the future, of course, we can change the timing of the Floquet pulses to basically engineer arbitrary X, Y, Z Hamiltonians. My final slide, I'd like to discuss briefly on what's next for us in the future. basically everything I've talked to you about have been quench experiments, where we do something very violent with the XY Hamiltonian and look at the quench dynamics. We're also interested in studying equilibrium states of matter, of course. So the theory predicts that if we prepare adiabatically the ground state of the XY model, we should be able to see a rotational superfluid appear, even for an imperfectly filled 2D lattice, even at our current filling fractions. Of course, the higher the filling fraction, the easier it is to see this rotational superfluid, the higher the critical temperature becomes. And in the future, we would also like to allow the molecules to tunnel between different lattice sites coherently. And with that, we can study extended Bose-Hubbard type physics. With that, I'd like to thank you for your attention.
The floor is open for questions. Over there.
Hi, thanks for the nice results. You showed in the anisotropic dipole-dipole Hamiltonian that there can be a cancellation at a certain angle of theta. Did you guys ever try tuning your quantization axis to that angle and seeing everything kind of hopefully turn off?
Yeah, we can already see where the dipole-dipole interaction cancels to 0. So this 1 minus 3 cos squared theta becomes 0 at around 55 degrees. And in the rightmost configuration, we had the B field tilted parallel to our plane around 9 degrees away from our lattice axes. So actually, at the 45-degree marker, you can think of the y equals x line here. You notice a bunch of white squares. Those are exactly where we would expect never to see any correlation buildup, because there should never be any long-range interaction. And we do kind of see that in our data. The y equals x diagonal is always much, much weaker.
Great, thank you.
Over there. Just continue passing the...
Hi, I enjoyed the talk, but you mentioned that the filling fraction is about only 15%, I believe, for the molecular states, and that affects your contrast in the HBT and the superfluidity experiments. But you have near unity transfer efficiency for sites that had both of the atomic constituents. So how exactly do you plan on getting that up, and how accessible is that?
Yeah, that's a great question. Let me go back to that. Right, so you see that our initial plan was to create dual Mott insulators, but this was technically very difficult. We had some number squeezing in our rubidium cloud. You see the peak filling is over 70%. We're not able to image sodium in our microscope, although we have absorption imaging. So we are not quite sure what our sodium filling fraction is. We suspect that it's much lower than a Mott insulator. And tricks that we can play to boost this are we can change how we generate a vertical lattice to increase the on-site intra-species U, so that we can push both more towards the Mott insulating regime. And then once they're both perfect Mott insulators, the rest kind of follows trivially. But a second strategy which we're thinking of is actually to create 2D bulk gases of molecules, as has been successfully shown in KRB with June, and also Sebastian Ville's group at Columbia University. And from there on, do evaporation so that you can get a degenerate 2D sample of molecules, and from there load a 2D optical lattice. So these are the two pathways that we're currently investigating.
Thank you for this great talk. I was wondering, for your coherence measurement at no density, you mentioned the T2 time is limited by the many body interactions. I was wondering, for molecules, exist some maybe dynamic decoupling sequence such that you can cancel these dipole-dipole interactions? Or could you use maybe multi-tone microwave frequency to dress your state, such that maybe if you want, you can turn off the interactions between them? Because I think they may have different sign contribution to your interaction strength?
Yeah, that's a great question. So I wouldn't say that we think our T2 is limited by dipolar interaction so much as the dipolar interaction has limited our ability to measure the T2 time. We can only maybe quote a lower bound of what it is. We don't really know the exact number. And you're absolutely right, there are dynamical decoupling schemes that can completely eliminate the dipolar effect. Just something we didn't try.
Yeah, thank you.
Bill?
Could you go to the plot, this is for the XYY model, where you were showing correlations, and one of the curves was a conserved quantity that was flat, and another one was decaying. Right, there we go. Now, when I look at the red points, I see as much oscillation, maybe even more, than there are in the green and blue points, if those are the right colors. I just had eye surgery, and I'm not sure I know my colors anymore. So what I'm wondering is that real? Or is it the usual thing where we deceive ourselves by looking at data and see patterns that don't exist?
That's a good question that I'm not really sure I know how to answer well. Certainly the oscillations are, it's not flat, you know, it's oscillating to as, like our error bars fall clearly outside of the static line at 1. It could be that our Floquet timings are, you know, not as precise as we would like them to be, although we don't really know the origin of
I see.
this
So that would
thing.
lead to some kind of like a beat between the stroboscopic observation and the,
Right. Although we did test that we were Floqueting rapidly enough by going to F and then 2F, and then we didn't see a difference there. So we thought we had approached the Floquet limit correctly, but yeah, this is unexplained.
yeah. Probably the chairman isn't going to allow me to ask.
No, you have time. We have 7 more minutes.
Oh, really? Oh, fantastic. Okay, let's go. Let's go to the Hanbury-Brown twist.
6 minutes.
Okay, so if I've understood correctly, what you're looking at is you've got the molecules, or you did it earlier with just the rubidium. I guess that's but you were looking at these things in the lattice. Then you release it, and then you're looking at what happens, you know, basically, you know, on a screen, except it's all, you know. So now, but basically what you're seeing is a diffraction pattern, right? And the information about the Hanbury-Brown twist correlations, if I've understood correctly, that's what I'm trying to, has to do with the relative amplitudes of the zero order diffraction compared to the other orders, or what? Maybe you could just explain it in a little bit more detail, where the information, because the spacing that you see here, that just has to do with what the spacing of the source looks like, because it's a diffraction pattern. So where is the Hanbury-Brown twist correlation coming, the G2 thing? Where is that information?
Right. I think ultimately it's always encapsulated by the initial source distribution. So we have, for instance, the larger the initial source distribution, the narrower the peaks we would expect to see. And of course, we need to be in the long time of flight limit. We need to let this time of flight occur for much longer than our inverse lattice trap frequencies, be in the far field regime, so to speak.
Sure, but that would be true of any diffraction, right? I mean,
Right.
you wouldn't need Hanbury-Brown twist correlations to know that.
Right.
So, but the fact that that the G2 of 0 is bigger than G2 of some long time, where is that in the, you know, how do you extract that from the data?
Sorry, the G2 of 0 is
Well, the
being
Hanbury
just
Brown
like
twist
the-
effect is that G2 of 0 ideally is 2 and G2 of infinity is 1. And so how does that feature, how do we see that feature looking at that data?
Okay, so basically what we're seeing here is the center point is kind of like a boring,
Right, that's
intensity.
that's the 0th order diffraction,
the 0th order diffraction, right? And in like stellar astrophysics, where you only have the source being one star far, far away, you don't see multiple peaks, right? But because we have this underlying periodicity of the source points, they're like Gaussian
Right, I would say you
distributed-
see like speckle. That's what you're looking at in Hanbury Brown twist
Right.
when you're looking at stars.
Right. Sorry, I'm not sure I understand your question.
we'll
but we can
discuss it later.
Yeah.
Thank you. So we have time for one last question, if there's anyone. Oh, yes. Thank you.
This is one of the I don't have the sense of scales question. So you were explaining the fact that depending on how you orient your magnetic field, you either have some donut star in the plane or some donut star out of the plane. And so in one case it's isotropic interaction, and the other case it's anisotropic. But I was wondering, it depends also a little bit on the phase of each of the donuts for the isotropic case. And I guess it would depend maybe on the electric field that there is. So is there a problem there? Are they always completely homogeneously rotating? And if it's not a problem, could that be like a resource to, like, I don't know, have an electric field gradient or whatever to change something about it?
Yeah, that's a great question I glossed over. So these donuts are kind of an inaccurate picture. What you should think of these are these fast spinning peaches that I
it's the
showed a
peach.
few
No,
slides
it's the
earlier. I just showed the donuts because they're
I'm
easier to
I'm with the
understand.
peach. I got
Right.
that. Those stuffs should have an orientation, and
Right.
that's the.
But the thing is, those are rotating in the lab frame at 4 gigahertz. That's way faster than any dynamics, any time scale that we care about. So we basically do see the overall average over, one rotation cycle. So the instantaneous phase of the wave function does not, to my knowledge, play a role.
Okay, and then the relative phase of two donuts does not impact the average? Maybe not. No, I guess not. No, it does not.
Right.
Yeah, so-
It's that.
Yes.
Yeah. Their phase is set by the local oscillator. Yeah.
Yes. Okay.
Very well. So thank you, everybody. So first, thank you, Zoe, for an excellent talk. And thank you for all the speakers for both sessions this morning.